Okay, so part 3 of permutations. We've seen that permutations are involved when order matters. So we'll do more arranging today, but we'll also look at more restrictions. We'll also see what happens when sets of objects have identical pieces to them. So in many problems, restrictions are placed on the order in which objects are arranged, and in this type, we always deal with restrictions first. First example, how many ways can the letters of the word oranges be arranged if there are no constraints? So there are 7 letters in that word, and they can be arranged in 7 factorial ways. Could also do this by using fundamental counting principle, marking down 7 spaces. There'd be 7 choices for the first letter, then 6, then 5. Those are all multiplied together. We've seen that that means 7 factorial, and you can do that on the calculator by going over to the probability tab. And 7 factorial is 5040. Part B, what if the first letter must be the letter N, which means you have one choice for the first letter, has to be the N, and there are 6 choices left, 6 letters left to arrange, and they can be done in 6 factorial ways. So 1 times 6 factorial is just 6 factorial. Try that again, which is 720. What if the vowels must be together in the order O first, A second, E third? So when objects have to be grouped together, here's how we do this. We'll mark down our 7 spaces. The O, A, and E in that order must stay together. So what that means is they count as one object to arrange. Right? If they slide over one space, they all slide over together. And you'd have the first space empty, then you'd have the next 3 filled, and then the last 3 empty. It doesn't matter how far they slide over, but they have to stay together. They count as one object to be arranged. So if these 3 letters count as one object to be arranged, plus we have 4 more, the remaining 4 letters, that gives us a total of 5 objects that are being arranged. And 5 objects can be arranged in 5 factorial, which is 120. Whenever objects have to stay together as a group, they count as one entire object to be arranged. So what's different between C and D? With C, it says they stay in that order, O first, A second, E last. Part D says they must stay together, but in no particular order. So this would have to be done in 2 different steps. The first step, like we did in Part C, the 5 objects are being arranged, and they can be arranged in 5 factorial ways. They stay together, they count as one object to be arranged, plus the remaining 4 letters gives us 5. However, in this case, you also have to multiply by 3 factorial. The 3 factorial represents the ways those 3 letters can be arranged amongst themselves. They can be in no particular order, so they can be rearranged amongst themselves, and 3 objects can be arranged in 3 factorial ways. So this will be 5 factorial times 3 factorial. 3 factorial is actually 6. 5 factorial times 6 is the same as 6 factorial, which is 720. We did that up above in part B. Or you could also use the calculator and go 5 factorial times 3 factorial. Same answer. It's equal to 6 factorial. Number 2 says 5 people, Shay, Reese, Caddis, and Matthew, Simone, are seated on a bench. And how many ways can they be arranged if Matthew must be seated in the middle? If we mark down our 5 spaces, There's only one choice for the middle seat. Matthew must sit there. You have 4 remaining people to be arranged. They can be arranged in 4 factorial ways. And 4 factorial is 24, I think. Yep. 4 times 3 is 12, times 2 is 24. So 24 ways that can happen. What if Shay and Caddison must be seated together? So again, whenever we have objects that must be kept together, they count as one object to be arranged. So those 2 people count as one object to be arranged, plus the remaining 3 gives us 4 objects to be arranged. They can be arranged in 4 factorial ways. However, we need to multiply by 2 factorial as well, which represents the ways that Shay and Caddison can be arranged amongst themselves. 2 ways, Shay first, Caddison second, or Caddison first, Shay second. 2 factorial is 2. So it's 4 factorial, which is 24, times 2 factorial gives us 48 different ways. Now, what if they cannot be seated together? I'm going to show you 2 ways that this could be done. So the first way, we'll call solution 1, would be found by taking all possibilities minus the possibilities with Shay and Caddison together. You see, there's only 2 things that can happen here. Either they are together or they're not. So if you take all the ways that they're together plus all the ways that they're not together, that will give you all the different possibilities for this scenario. So one way to get this, the number of ways that Shay and Caddison cannot be seated together, would be to take all possibilities, which would be 5 factorial, minus those possibilities with Shay and Caddison together, which we found in part B was 48. So 5 factorial is 120 minus 48 gives us 72. So that would be one way to get this answer. The number of ways that Shay and Caddison cannot be seated together could be found by taking all possibilities minus those possibilities with them together. Here's another way that this question could be done. Solution number 2. So if they cannot be seated together, we'll mark down spaces for the other 3 people. And notice I've left room in between those spaces. Below, I'm going to mark down some blue spaces. These are the spots that Shay and Caddison could be put in. If they're not together, that means there has to be another person in between them. So these blue spaces represent places where Shay and Caddison could be put. Now, there's only 2, Shay and Caddison, but there's 4 different places that they could be put in. So 2 of them will be filled, the other 2 will be empty, but it doesn't change the fact that these are the number of places that we could put them. So to get our answer, here's what we do. We take the 3 factorial, which will represent the ways those 3 remaining people could be arranged. Okay? As well, now we'll talk about the way that Shay and Caddison can be placed. For that first person, whether it's Shay or Caddison, doesn't matter, there are 4 choices, 4 places that they can go. So we're going to multiply by 4. And then there's 3 spaces for the remaining person to be placed. Whether it's Shay or Caddison first doesn't matter. Let's say it's Shay. There's 4 places that Shay can be put. And then there's 3 places for Caddison to be put. So the answer will be found by going 3 factorial times 4 times 3. 4 times 3 is 12. So we can go 3 factorial times 12. Gives us exactly the same answer, 72. So 2 different ways to get that answer of 72. On the next page, how many different 3-digit even numbers greater than 300 can you make using the digits 1, 2, 3, 4, 5, 6 with no digits repeated? So we're going to make 3-digit numbers, so we'll mark down 3 spaces. And before I even do this part, there's 2 different scenarios that you have to look at. The first scenario would be if the first digit is even. The second scenario, so I'm going to put or there, would be if the first digit is odd. And the reason we need to do this is that the 3-digit number has to be even. Well, that means the last digit has to be even. Also, the number must be greater than 300. So if that first digit is a 4 or a 6, because the first digit the number has to be greater than 300, which means that the first digit has to be either a 3, 4, 5, or 6. But if the first digit is a 4 or a 6, that's going to limit how many choices we have for the last digit. The number must be even, so the last digit has to be even. There are 2 restrictions we have to look at here. There's a restriction on what the first digit can be. There's also a restriction on what the last digit can be. But again, if the first digit is even, that's going to limit how many choices we have for the last digit. But if the first digit is odd, there are fewer restrictions or fewer, restrictions on what that last digit can be. Okay, so that's why we have to do 2 scenarios here, because depending on what the first digit is, it will affect what the last digit is. So if the first digit is even, excuse me, in this case, that means either a 4 or a 6, because the number itself has to be greater than 300. There are only 2 digits that are even that are greater than 3 in this case. So there's our first restriction we're talking about, what the first digit is. So now we'll look at our other restriction, which is what the last digit is. The number must be even, so the last digit must be even. Originally, we had 1, 2, 3 even digits to choose from, either the 2, the 4, or the 6. But we've already used one of them for the first digit, so now there's only 2 choices for the last spot. We started with 6-digit, we've used 2, that means 4 remaining for the middle spot. There's no restrictions on what the middle number can be. So 2 times 4 is 8, times 2 is 16, or means to add. Now, what if the first digit is odd? That means either a 3 or a 5. So again, there's 2 choices for the first digit. Our other restriction is what the last digit can be. And we haven't used any even digits yet, so we have 3 choices for the last digit. Again, there's no restrictions on the middle. We started with 6, we've used 2. That leaves us with 4 for the middle. 2 times 4 is 8, times 3 is 24. And again, the word or means to add. So our answer is 40. There are 40 different 3-digit even numbers that are greater than 300. So now let's talk about permutations with repeating objects. Consider the number of 4-letter arrangements using the letters from the word pool. So obviously you have the O's that repeat. And so if you look on the screen, you can see that the first O is one color, the second O is a different color. So we've got our first row. There are 12 possibilities there. The row beneath that, the only difference is that the colors of the O's have switched because they have been switched around. But in the end, it's the same result, the same permutation of letters. So in this case here, we'd only take either the top or the bottom for the number of different four-letter arrangements. If you take out the color coding, the top row and the bottom rows are the same. So if all of the letters were different, there would be 4 factorial or 24 possibilities. But in this case, there are 2 identical letters, which if they were different could be arranged in 2 factorial ways. So to get the answer from only one row, which is 12, you can take the 4 factorial, because there's 4 letters, and then divide by 2 factorial, because there are 2 identical letters. That will give you 24 divided by 2. That'll give you your answer of 12. The number of different permutations of the letters of the word pool. So if you have a set of n objects, of which A of one kind are identical, B of a second kind are identical, and C of a third kind are identical, and so on, then those can be arranged in n factorial. N is the original number of objects divided by A factorial times B factorial times C factorial, etc. Where A is the number of items that are alike of one kind, B are the number of a second kind that are alike, and so on. So, how many different 8-letter arrangements can be made using the letters of the word aardvark? There are 8 letters in this word. However, there is repetition. There are 3 A's, so we have to divide by 3 factorial. There are also 2 R's, so we also must divide by 2 factorial. When you do this on your calculator, you have to keep the denominator together, meaning you got to use brackets for the denominator. 8 factorial divided by, and then in brackets, 3 factorial. And we can just go times 2 because that's what 2 factorial is, but you have to keep those in brackets to get the answer, 3360. And so there's our answer. How many different 5-digit numbers can you make by arranging all the digits of 17171? Again, this is repetition. There are 5 digits there, so they could be arranged in 5 factorial ways. However, there's repetition. There are 3 1s and 2 7s. So you have to divide by 3 factorial and 2 factorial. So once again, we need to use brackets here. 3 factorial, which is 6, times 2 factorial, or 2. Whoops. Gives us 10 different arrangements of those 5 digits. So you can also use this same process for these pathway questions. How many paths can you follow from A to B in a 4x6 grid if you may only move up or to the right, which means you're always moving closer to B? So this is an example of pathways with repetition. So here's how this would work. You're going to count how many, so we'll consider this to be like a grid in a city. So each time you move, you're moving another block. But you don't start counting until you move. So from A to B, I'm going to go straight up and to the right, and this is just counting how many blocks we have to travel. Remember though, you don't start counting until you move. So starting at A, there's your first block. And we'll continue. Second, third, fourth, 5th, 6th, 7th, 8th, 9, 10. You have to travel a total of 10 blocks. And it doesn't matter what route you follow, it'll always be 10 blocks. So we could have gone to the right first and then up. It would have been 10 blocks. We could have zigzagged through any different route. It would have been 10 blocks all the way. So that can be done in 10 factorial ways. However, there is repetition here. And the repetition comes by the fact that there are, and again, remember, you don't start counting until you move. There are 1, 2, 3, 4 streets that are going in the same direction, west to east. You don't start counting until you move. That's why you're not counting that bottom one. Okay? You see, if you did go to the right first, then that would eliminate the top row, the top street. Okay? So you don't start counting until you move. So therefore, there are 4 blocks that are going in the same direction, 4 streets that would be going west to east. So we will divide by 4 factorial. And there are also streets that are going in the same direction from south to north. And again, you don't start counting until you move. So 1, 2, 3, 4, 5, 6. You don't start counting until you move. So that's why we didn't count the first one from A going straight up. Because if you did that, you would eliminate the last one. So you're only going to count one of them. And again, you don't start counting until you move. So that gives us 6 factorial because those blocks represent repetition, going the same direction from south to north. If you do this on your calculator, 10 factorial divided by, in brackets, 4 factorial times 6 factorial. We'll get our answer, 210. That's how many different routes or different paths that person could follow to go from A to B, always moving closer to B. Later on this week, we're going to see a couple different ways that we could get this same answer. One of them is using combinations, and one of them uses something known as Pascal's triangle that we'll see towards the end of this chapter, what Pascal's triangle is. It has different applications. This is one of them. Okay? How many different 3-digit numbers can you make using those digits if repetitions is not allowed? So in this case here, there's 2 different ways we could do this. One of them using the fundamental counting principle. Remember, fundamental counting principle is an example where order matters. We're only arranging 3 of these 5 digits. So that's why I marked down 3 spaces. Repetition, though, is not allowed, which means you'd have 5 choices for the first digit, and then 4, and then 3. Using the fundamental counting principle, 5 times 4 is 20, times 3 would give us 60 ways. Or we could also use permutations. We could go 5p3. That would work as well. So remember 5 and then go to math over to probability. Number 2 in this list is NPR. So we choose that, then we put our 3 there for 5p3. Gives us the same answer. Gives us the same answer. Okay? Part B then says how does the application of the fundamental counting principle in Part A change if repetition is allowed? Well, if repetition is allowed, we'd mark down our 3 spaces, and there would be 5 choices for each one, which is 125. Obviously a much larger answer. This also again tells us that if repetition is allowed, you cannot use permutations. You cannot use NPR. Permutations is used, NPR is used if order matters, but also if there is no repetition. It cannot be used if repetition is allowed. All right, question A on the next page, evaluate that using factorial notation. So we did some of this last week. 7p2 means 7 factorial over 7 minus 2 factorial. That's the NPR formula, and it's on the formula sheet, so don't have to memorize it. So we'll get 7 factorial over 5 factorial. And we can simplify this by expanding the top, but we would stop the last factor in the progression would be a 5. Remember, the last factor when you're expanding has a factorial on the end, and the reason we stop there is because that's what the denominator is. They will cancel. And you're left with 7 times 6, which is 42. And that could be checked on the calculator. If we went 7p2, you get that same answer, 42. So it checks. Question B, we saw one like this last week. Show that 5 factorial minus 3 factorial is equal to 19 times 3 factorial. So we did this last week by expanding and taking out a common factor. 5 factorial would be 5 times 4, and I can go all the way down to times 2 times 1, but I'm going to stop at the 3. Remember, the last factor in the progression, in the expansion, always has a factorial on the end, and the reason I stop there is because that matches the second term here. Both of these terms have a common factor of 3 factorial in them. And if I take that out as a common factor, I'm going to be left with 5 times 4. That's what I'm left with when I divide that first term by 3 factorial, minus when you divide the second term, which is 3 factorial by itself, you'll get 1 there. So that'll be 3 factorial times 20 minus 1, which is 19. So there we've shown that the two sides are equal. It doesn't matter whether it's 3 factorial first times 19 second. Order doesn't matter when you're multiplying things together. All right, and C asks us to solve for NP2 equals 56. And we saw last week that this could be done by trial and error, by guess and check. But if you see something like this on the diploma exam, it would say determine the solution, or algebraically determine, which means you have to show your work. And that would be done using the NPR formula on the right side. And by expanding the top, n bracket, the next factor is 1 less. And again, we can keep going on forever in this case. But we would stop with an n minus 2. Again, the last factor in the expansion always has a factorial on the end. And the reason we stop there is because that's what the denominator is. And they will cancel. The n minus 2 factorials will cancel. So we're going to get a quadratic here. When you multiply out what's left on the left, it'll be n squared minus n. We'll bring the 56 over, make it equal to 0, because we always do that to solve by factoring. The factors will be n minus 8, n plus 7. So according to this, n would equal positive 8 and negative 7. But n, which is the number you're choosing from, can't be negative. That is extraneous. So n equals 8 is the only answer. If we go 8p2, we should get 56. And we do. So it checks. It checks. In how many ways can one French poster, two math posters, three science posters be arranged in a row on a wall if the two math posters must be together on an end. This is another one of our scenario examples because they could be on the left end or the right end. So we have to do both scenarios, and remember the word or means to add. So if they are on the left end, you've got a total of 6 posters here. If they're on the left end, that means the first 2 positions. But you also have to remember that those 2 can be arranged in 2 factorial ways. The posters are different. They're not identical. And it doesn't say that specifically on a diploma exam, though it would. It would be clear. So you have 4 remaining posters. They can be arranged in 4 factorial ways. Or means to add. If they're on the right end, that means you'll have 2 factorial at the end and 4 factorial at the start. Doesn't really matter though, because order doesn't matter when you're multiplying. 2 factorial, which is 2, times 4 factorial, which is 24, should give us 48. Yeah. So it's 48 and 48, a total of 96. There's the answer. Part B, what if the 3 science posters must be together? So it just says together, not on one end. Remember, when objects have to stay together, they count as one object to be arranged. So you have a total of 4 items to be arranged here. The 3 science posters together count as one object plus the remaining. There's 4 things to be arranged, which is 4 factorial. However, we also have to multiply by 3 factorial, which represents the number of ways the 3 science posters can be arranged amongst themselves. So it'll be 4 factorial, which is 24, times 3 factorial, which is 6. So it should be 24 times 6. 144 is the answer. What if the 3 science posters cannot be all together? So to do this one, I will do the way we did one earlier if we take all possibilities minus the possibilities with the science posters together. And this is especially easy because we already found in part B the number of possibilities with the science posters together. It's 144. All possibilities here would be 6 factorial minus what we found in part B, the possibilities with the science posters together. That's 144. Will give us an answer of 576. Now, when we did that one earlier with the 2 people that couldn't be together, I showed you another way by marking down spaces. That could be done here, but it'd be a little more complicated. In that case, there were only 2 people that had to be separated. In this case, there has to be 3 science posters that have to be separated. What makes this more complicated is the fact that you just can't have all 3 together. So you'd have to do 2 different scenarios. The first scenario with all 3 separate. The second scenario would be with 2 separate and 1 not, meaning 2 together and 1 away from it, is what I meant to say. Because that's still not all 3 together. So you'd have to do those 2 scenarios with the spaces and then add them up. And it would work. You would get the right answer of 576. It's just much more complicated. This way is much easier. All possibilities minus the possibilities with the science posters together. So we've talked about arrangements with cases before. We've done them, and this is where you have the word or. To solve some problems, you must count the different arrangements in cases. For example, you might need to determine the number of arrangements of 4 girls and 3 boys in a row of 7 seats if the ends of the rows must be either both male or both female. So we've done these before, right? And remember that the word or means to add, so you have to add them together. How many 4-digit odd numbers can you make using digits 1 through 7 if the numbers must be less than 6,000 and no digits are repeated? So again, because you can only use 4 digits and it has to be odd, that tells us the last digit must be odd. The other restriction is it must be less than 6,000, which means that the first digit can either be a 1, 2, 3, 4, or 5. But if the first digit is odd, then that will take away one possibility for the last digit. If the first digit is even, though, it doesn't take away a possibility for the last. So those are the two scenarios that we have to look at. The first digit can be even, which won't affect the number of choices for the last digit, or the first digit could be odd, which will affect the choices for the last digit. Again, the word or means to add. So we're doing 4-digit numbers, so we'll mark down 4 spaces for each scenario. The number has to be less than 6,000, so the first digit has to be less than 6. That means for the first scenario, there's only 2 choices for the first digit, the 2 or the 4. The first digit is even. If you look at the digits 1 through 7, the last digit has to be an odd digit, so it could be a 1, a 3, a 5, or a 7. 4 choices for the last digit. We started with 7, we've used 2, that would leave us with 5 choices for the second, and then 4 for the third. If you multiply, 2 times 5 is 10, 4 times 4 is 16, 10 times 16 is 160. Again, or means to add, and now, how many ways can you do this if the first digit is odd? Because the number must be less than 6,000, in this case, it could either be a 1, a 3, or a 5. 3 choices. But now we have to move to the last digit. In order for the number itself to be odd, the last digit must be odd, but we've already used one of them for the first spot. Originally, we had 4 odd digits to choose from, 1, 3, 5, or 7. We've already used one now, so there are only 3 choices for the last digit. We started with 7, we've used 2, again that leaves us with 5 times 4 for the remaining 2 digits. 3 times 5 is 15, times 12 will be 180. When you add those together, you'll get 340. So there's the answer. All right, your assignment is on page 525, question 8, as well as 10 through 15. You're going to hand this one in. Right, so you need to do this one and get it handed in for marks. You'll be able to check your answers at the back of the textbook to make sure your answers are correct, but obviously you have to show where it comes from. Okay? So we'll spend a couple days on combinations, a couple days on the last section, which is binomial distribution and Pascal's triangle. So basically at the end of this week, we'll be done this chapter. That means the following week, you'll have a quiz on chapter 11, your exam on chapters 9, 10, and 11, and then we'll be reviewing for the diploma. Okay?